Thank you very much. Thanks everyone for being here, for making sure that we get back from our coffee break. I'm going to take some time to sort of get into the subject that I want to talk about, which is going to be brittle and ductile yielding. As I typically tend to do, I want to acknowledge that even though I'm the one telling the story, what I'm about to tell you, the understanding that we've developed, has really come about through conversations with almost everybody that I work with. I find it very difficult to separate where ideas come from when you have so many conversations with so many talented students and postdocs and so on and so forth. So I've highlighted three former grad students here. The work is specifically work that I did with Krutaf before he graduated, but it came about from work that Johnny started and Gavin continued. And so I want to just acknowledge them before I get into it. Okay, so now I want to get into the meat of the subject, which is yielding. Okay, so yielding is seen in many processes in industry and the environment. Really what we're talking about is a change of material behavior from that of a solid to that of a liquid. There are many instances in which we see yielding and in which yielding is important. So things like pastes for screen printing, if you're making chips and things like that, personal care products. Personal care companies spend millions of dollars making sure that they get the yielding characteristics just right so that they can sell you as much water as they possibly can. Foods are also really interesting in terms of their yielding behaviors. I say this a lot. Your mouth is probably the most sensitive rheometer that you will ever use. When you stick food into your mouth, you can tell instantly whether the ice cream is expensive or cheap. You can tell exactly the textures that you're after. There are lots of biological materials that are yield stress fluids and that their yielding behavior dictates their function. And tons of industrial materials, literally tons. I also like to focus on the fact that soils and muds are also yield stress fluids, and the idea of yielding when it comes to soils and muds is not just of academic interest, it's of civil engineering interest. And I had a project with Sandia National Lab where this was a national security issue, right? So this is the sort of thing where we want to understand what would happen in mudslides to be able to predict the behavior of muds. And you can see that this is really fluid-like in terms of flowing over this rock. And so understanding the yielding characteristics of materials is therefore really, really important. And I want to start this conversation with sort of situating where I'm going. And I want to situate it by asking, how have we modeled yielding? And really this is a discussion on how has our understanding of yielding developed and how we write it down mathematically. So we typically go back to the work of Schwerdoff and Bingham, where we have, this is the figure from Bingham's paper, where he saw that you had to exceed a critical pressure before you got any volumetric flow rate. And so this then became a discussion where the stress was equal to a yield stress plus the Bingham viscosity times the shear rate. So again, there was no flow below the yield stress. Herschel and Bulkley extended this with some sort of power law flow. Casson had a separate version. But these all describe a rigid material below the yield stress, and they only deal with the material behavior above the yield stress. So they don't tell us anything about the yielding process itself. They simply describe how the material flows once it has yielded. And again, the stress in all of these cases is described as the sum of a yield stress and some flow rule. That's the way that we think about it. Then we go to Oldroyd's work. He was one of the first people, along with Prager, to really think about what happens below the yield stress as well. And this is a copy from his paper where he described it. His nomenclature is a little different. But what he's saying here, these P's are stresses, mu here is an elastic modulus. So below the yield stress, he's saying that the material behaves as an elastic solid, and then above it, it flows like a Bingham plastic, right? And so he had this two-regime idea that I'm going to refer to as the Oldroyd-Prager formalism, because these were the two groups that first sort of put it together. And one of the really interesting things that Oldroyd stated, if you go back and read his paper, is he states in the quasi-static approach to the yield stress from below, which is to say he was only ever considering what happens when you go really slowly up to the yield point. So again, he was not trying to say anything about the yielding process. He was saying if I go infinitesimally slowly, then below it's an elastic solid and above it flows this way. Okay? But this idea of the two regime behavior has persisted in our understanding of yield stress fluids since. The next two models I'll highlight, one from Pierre Saramito. Again, he fixed some issues with Oldroyd's description, and he ended up describing yield stress fluids as being viscoelastic below the yield stress. And this is taken from Saramito's paper, where you've got a digital yielding element here. And so below the yield stress, you've got this Kelvin-Voigt viscoelastic solid. Then once the yield stress is exceeded and this digital element breaks, then you've got something that looks like an Oldroyd type or a Jeffreys type model. And then where I'm going with this today is some work that my student Krutaf and I published, where we end up with a relaxation time that's rate dependent. And that's what accounts for yielding. So we're starting to then gain an understanding, rheologically speaking, about what yielding looks like. Right? So we have this rate dependent relaxation time. I now just want to make a blanket statement. This was sort of alluded to by Suzanne's question before to Jim. How do you define yielding? You know, yielding is difficult to define. It's difficult to identify. And this was nicely summarized by Dinkery, Paredes, Den, and Bond in their paper on different ways of measuring the yield stress. And these are some of the methods that they list. And you can see that it depends on the type of experiment that you do. Or another way of talking about it is they're saying that the measures that we have reported in the literature are dependent on the kinematics of the experiment that we have used to determine them. Right? So you can use a steady shear test, which is what we saw from Bingham. You can use steady shear startup. We'll talk about that in a bit. Oscillatory tests, if you do an amplitude sweep, there's something like 8 or 9 different measures that people have reported as the yield stress from the same experiment. So you could give the same data to 2 different groups and you might get 6 different answers of what the yield stress actually is. Right? We can also talk about creep tests in terms of viscosity bifurcation. Right? But I like to think about how we identify yielding in terms of observations. And so, again, we go back to Bingham's original work, and we can think of the non-zero stress at the very smallest shear rates that we measure. This is almost independent of the way that we approach it because it's now in the static limit, right? There's no transience to the kinematics here. This is work from Philippe Cousseau and Daniel Bond, where what they did was they had some yield stress fluid. I think this was a clay. They stuck it on a sort of, this purple is sandpaper, and then they slowly inclined the plane. And what you would expect if it was a Herschel-Bulkley material is some particular type of slow increase in the flow. And instead what they saw was an avalanche, that when you got above a particular critical angle, you saw this rapid racing downhill of the material. So it wasn't yielding slowly as you might expect from the steady state experiment. It was avalanching, and then this is what we see when you apply creep tests and you impose a constant stress. You'd see that for stresses below the yield stress, your viscosity bifurcates, and so it looks as if it starts to flow and then it sort of halts. And then when we get to the amplitude sweeps, the oscillatory tests where you slowly or you gradually increase the amplitude of the deformation, and you plot G prime and G double prime, which are commonly thought of as elastic and viscous properties or solid and liquid-like properties. We'll get to the nuance in that interpretation in a sec. There's typically an overshoot observed in G double prime, which is therefore somehow associated with yielding. Many people would measure the crossover point. Some people will take the point that deviates from linearity. There are all sorts of other measures in here. Okay? But the point is that this doesn't really deal with yielding. This deals with what happens once the material has yielded. These two experiments, or these types of experiments, deal with the process of yielding itself because there's some transience involved. And now we get to the topic of the talk, which is really that not all yielding is the same. We acknowledge differences in our steady shear startup experiments where you sometimes see overshoots in the stress. And sometimes the overshoots are rate dependent. As we see here, this is the same material, low rates and high rates. And you can see as you go to higher rates, the overshoot seems to disappear. You can see overshoots in some material at higher rates and not at lower rates. This is work, I think, from George Pedakidis. No, this is actually work from, this is George's work, I think, where you see these rate dependencies. They're also age dependent, as Suzanne has shown a lot as well. When you go back to the idea of creep experiments and you impose a constant stress, some materials show what we call delayed yielding, where they look like they're not flowing for a long time. This is the strain. They look like they're not flowing for a long time, and then at some long time, they just appear to start flowing, and it appears as if it's out of nowhere. And so this is work from Spraker et al., from Dave Waits' group, where they investigated a large number of different materials that show this delayed yielding, and I'll come back to that as well. And in terms of our oscillatory tests, when we do amplitude sweeps, you can have a smooth or an abrupt overshoot in G double prime as well. And these are typically referred to as sort of ductile and more brittle type yielding. And these overshoots are typically associated with more brittle yielding. And I'm going to use this language of comparison. And I want to sort of reference Wilson Poon here, who, when we were at a workshop in Leiden at the beginning of last year, 2 years ago? He suggested, rather than trying to say this is ductile and this is brittle, why don't we just refer to material responses as being slightly more brittle or more ductile? And so the way that I'm starting to think about this, and the way that I'm going to carry on talking about it today, is that brittle to ductile it's a spectrum of behaviors. Okay? And we're going to start talking about brittle yielding as being more brittle than something else. Okay? Sure.
The overshoot sometimes is rate dependent. Isn't it always rate dependent?
So really what I mean is the size of the overshoot will be rate dependent. Some people don't report a range of rates, which is why I don't want to be absolute. Okay, so now that we've had that introduction, I really want to cut to the chase of what we've learned in the last few years and then show where we're going with our thinking on this. So I want to say just new experiments have changed how we think about amplitude sweeps and yielding in general. And so the experiments that we do acknowledge the fact that strain is a composite parameter. It can be measurably broken into recoverable and unrecoverable parts. We always learn this when we start learning rheology and we learn about creep experiments, because we don't just learn about creep experiments, we learn creep and recovery, right? The and recovery is always the second part of the creep experiment, where you go to zero stress and you measure how much of the strain is recoverable. There is no reason that we cannot measure recoverable strain under every protocol that we typically apply when we're performing a rheological characterization. And so the experiments that we've done, focusing on the oscillatory shearing, are exactly that. We get to steady state in our oscillatory test, and at the moment we want to know the recoverable strain, we go to zero stress, and we measure how much of the strain is recoverable, and then what's left is, by definition, unrecoverable. And then what we do is we go to steady state again, and at T plus dt, we do another recovery experiment. And so gradually then we build up our transient understanding of how much of the total deformation is recoverable and unrecoverable. Okay? So that's really the idea. For the technicians, what we do is we do the same thing in reverse so that we then get rid of any instrumental drift. So we repeat this multiple times per period in the forward and the reverse direction, and we take an average. Yeah?
The difference between recover and the protocol you use, once again.
Yeah, so in this case, we just do our regular oscillatory test until we get to steady state.
Yes.
And then at the start of the period, I will go to zero stress, and I let the material recover. Okay, and I just measure the recovery. Then I go to steady state again, And at the start of my period plus dt, I do another recovery experiment. So I just simply do, the gray point would be the start of my period. This first green point is now t plus dt. It's my second experiment, but I was still at the same steady state. So it's a measure of how much recoverable strain there was in the system at the point that I went to zero stress. And then I just iterate through performing, in this case, 33 different experiments for one amplitude. And then I do it in the reverse direction, so I do 66 experiments for one amplitude. Then I do another amplitude. And then I do another one. And I build up my amplitude suite. My students didn't like it when I first told them. What's that? Sorry?
The frequency of your oscillation?
Oh, you do whatever frequency you're interested in. In this case, this is at 1 radian per second. But this works for any experiment that you want to do.
Yeah, when we study the reversion of flow, for example, in numerical simulations. So we go to steady flow, and then we go back to zero stress and reverse. And then we see that when you go down from your flow in AQS, so in that case, we kill all the time dependencies. And then we see that between the flow, when we drop the stress to zero, there are events taking place. There is some plasticity. Maybe it's small, but it's non-zero. And so from that standpoint, I mean, how legit, for me, it's not clear how legit it is to define the residual stress as the stress when you revert the stress to zero, whereas you could also say, for example, that you are in a flow and you stop the stress at its value and look at the recoverable strain at the current stress.
Yeah, absolutely.
And that would be different.
Absolutely. In fact, I think they will be different, and I'll explain to you why I think they'll be different, because the strain history will be different between a stress-controlled and a strain-controlled protocol. And my entire point is that whatever protocol you're interested in, you can do recovery tests, and you can determine how much of the strain is recoverable and unrecoverable. There's no...
So you could identify the residual strain at the flow stress.
Yes, absolutely. We do. Yeah.
I mean, do you have in mind that assist? I mean, so is this a measurement that I can do where post yield I will be in a fluid state?
What do you mean post yield? We'll get to this. Yeah, that's exactly right. Yeah. So give me your question again at the end, and we'll address it. Yes.
The quick question was, is it also something that could apply to elastoplastic flow?
Yeah, absolutely.
Okay.
Yes, I agree. Yeah. Okay, so this is the protocol that we do. And what we find, I'm going to cut to the chase here, is that the overshoot that we typically see in G double prime for yielding materials always comes from the acquisition of unrecoverable strain. So because we've got two strains, we've got recoverable and unrecoverable strains, we also have two rates. You have the rate at which you acquire strain recoverably and the rate at which you acquire it unrecoverably. That means that G double prime is also a composite parameter, because now you can dissipate energy via recoverable processes, such as a change of conformation without your center of mass changing, and you can dissipate it by unrecoverable processes like a center of mass motion. Right? And so this is how we break it down. We'll come back to these definitions in a bit, because this is really an average energy dissipated by recoverable processes. This is like a Kelvin-Voigt type energy dissipation, and this is like a Maxwellian type energy dissipation. And so across a range of materials, we see that the overshoot in G double prime always comes from the acquisition of unrecoverable strain shown in cyan. And what I want to point out here is that we're seeing some smooth overshoots and some rather abrupt overshoots. So there's a difference between ductile and brittle type responses. And if we have a look at what's happening sort of microscopically or microstructurally, for this xanthan gum, we've got locally stiff configurations. These biopolymers have sort of collapsed into sort of hardish colloids, but globally it's quite soft. We've still got a gel here that's around 100 Pascal or so. For our concentrated Ludox, this is exactly the same stuff that Jim was showing us before the coffee break. Locally, it's stiff. These are hard silica particles, but again, globally soft. And then for the Carbopol, this is a microgel. It's locally soft and globally soft. And so the difference that I want to say is this is ductile, these are brittle. These distinctions will come in when we start to formalize that idea. Okay? So if...
What is the time derivative of the recoverable strain, given that it is the plateau value after a...
So it depends on the system. And
how is this operationally defined? I thought the gamma recovery was, you set the stress to 0, you wait for the system to relax, so it's a plateau value. So how does it have a time derivative?
Right. So what I'm talking about is the ultimate recoverable strain at that point. Then when I do my next point, I get a different value of the ultimate recoverable strain.
Time derivative, in the time evolution, you just look at it as a function of the period, time period.
I would say that it is an actual representation, an actual time derivative, because the experiment that we're thinking about is that during the experiment, there is a recoverable strain that's changing during your experiment, and we're just making a measurement of it. Yeah? Okay, so let's now go back and have a look at some of the measures that we saw before and see what they can do in terms of our understanding of yielding in terms of the model. So if we go back to the data that I just showed you, this is now for Carbopol. So we've got G prime and G double prime with the two components. I'm just highlighting here the definitions of G double prime, right? So we've got what I'm calling G double prime solid, that's energy dissipation from recoverable processes, and G double prime fluid, energy dissipation from unrecoverable processes. And what I want to highlight is that the normalization factor here is the total strain amplitude. It is not the recoverable or the unrecoverable amplitude. We're normalizing by the sum of the recoverable plus the unrecoverable strain, right? That's what that amplitude is. So if we renormalize, and we renormalize to the amplitude of the recoverable and the unrecoverable strains, our amplitude sweep now looks like this, where the yellow parts are the recoverable processes. So this is G prime and this is G double prime from the solid part, the recoverable part. And the cyan part is the unrecoverable part. And I've stuck a solid line through this part of G double prime fluid that's been renormalized. And that solid line is my steady shear viscosity that I measure from the flow curve, from which all transients has been taken out, which therefore says that when I renormalize like this and I'm measuring the recoverable and unrecoverable parts, I'm getting access to the steady state information. Furthermore, you'll note that I'm plotting against the total strain amplitude still, which says this is, remember, the sum of a recoverable and an unrecoverable strain, and yet this is my steady state flow curve. So what that tells me is that the rate at which I acquire strain recoverably assists in yielding. That's what this expression here is saying. It says that the faster I acquire strain recoverably, the more that affects my yielding behavior. And so what we can then do is we can add together the recoverable and the unrecoverable parts. This is exactly how you would go through and derive the Oldroyd equation to begin with. We've got something that looks very Oldroyd-like, except now our flow viscosity is dependent on the total strain rate, not just the strain rate that you would have across the unrecoverable part. And it means that we've now got a rate-dependent relaxation time. So at low rates, our relaxation time is really high, as if it were a solid-like material. And at high rates, our relaxation time is low, as if you've got a liquid material. So now we're starting to think about yielding as a change in the instantaneous relaxation time from a solid to a liquid, which is why we get the smooth transitions. Right? So we've got this rate-dependent relaxation time, and if we put together a full tensorial version of the model, we can also predict the normal forces, and what we predict is that our first normal stress difference is 2 times the square of our shear stress over the modulus, which is exactly the same thing that was found by De Cagny et al. From Journal of Rheology in 2019, when they measured what they called the normal yield stress. But if we go back to just the 1D version, we've got a single equation describing the yielded and unyielded behavior. So this is now an alternative to the old Royd-Prager formalism that separated the physics. Right? Now we've got the same physics occurring both below and above the yield stress, and there's no abrupt yield point. So let's see how this does. If we have a look at our amplitude sweeps, the symbols are experimental data, the lines are model predictions, including the different contributions to G double prime, the solid and the fluid-like parts. So we get the smooth overshoot predicted, we even get the right components, and there's no abrupt yielding. Yielding is a continuous process across here. So any particular singular point that you want to choose as the yield point here is an oversimplification of the kinematics that are taking place from the transient kinematics of the oscillatory experiment to a yield stress constitutive relation that has a single well-defined yield stress. And if we want to have a look at the transient Lissajous figures, these are our experimental ones, and this is the model predictions below. So just from our understanding of the average behavior, we get the transient behavior nicely organized as well. And so this particular form of the model therefore predicts our steady state flow curve behavior. It also, I haven't shown you yet, predicts avalanches and gets our smooth overshoot. But this is now the second part. Oh, Thomas, you want to?
So my question is, if you had to draw what's happening in the solution, what would be your drawing?
Super.
Are there some motile part, non-motile part?
Yeah.
What is happening?
This goes back to Anael's question before. Let's talk about that in the discussion because it's far too long for the time that I have at the moment. So now we get to the sort of the second part of the talk, which is that some materials appear to be more brittle than others, and can we describe those? So here's the behavior of the Ludox sample that Jim was talking about before. G prime and G double prime. And I'm showing the results of the model predictions right on top, where we've got the smooth overshoot in G prime, which does a horrible job at small amplitudes. It's grossly over predicting the yielding behavior, and it gets the components terrible as well. So here's now the conceptual step that I want to take. So in our model that I've shown you so far, plasticity is enhanced by rapid elastic deformation. Now I want to say if the structure is locally stiff compared to the bulk, then I'm going to hypothesize that long-range elastic deformation is more suppressed, because the way that I think about it is if you've got a shear deformation locally, that's then going to propagate a strain field throughout the material. This is very much like the correlation length work, and I don't know yet what the connection to that is, but I have a feeling that it's there. And so if we've got something that's locally stiff, then it doesn't deform as much, and so long-range strain is therefore suppressed, and so the small amount of energy that you need to flip a plastic event somewhere else is going to be less likely if you've got a locally stiffer material compared to the globally soft, right? So I'm going to say that we can describe brittle soft materials as ones that have a smaller contribution to plasticity from elasticity. So what that means mathematically is that I simply change my flow viscosity that describes the unrecoverable behavior that was previously just the sum of the recoverable and the unrecoverable rates. And now I'm reducing the amount that plasticity is enhanced by elasticity by a factor of BT that I'm going to call the brittility factor. Right? So it means that if you look at this, I've now got a different effective rate dictating my plastic behavior. So the total rate will always be the sum of the recoverable and the unrecoverable behavior, but the rate that the material feels will be reduced by a small factor that I call this brittility. And I'm going to hypothesize that it's a ratio of a local modulus to a bulk modulus. We have in the paper an example where we took someone else's data where they had measured TEM, or they had done some AFM measurements actually, and they'd measured a local modulus, and then they'd measured a bulk modulus. We put those values in here and we accurately predict their rheology. I'm not going to show that now, but that's just to say that this hypothesis worked at least once. The best I got. So you got to be honest. Okay, so this is now what I mean by the brittility controls the extent of non-locality. This is going to be a bit chewy, so I might get through this kind of quickly. So again, I'm suggesting that it's a ratio of a local to a bulk, and this is the idea that we had before that I was trying to explain, that when you've got soft local structure, the strain field can propagate further than if you've got stiff local structure. And that means that if you've got a local structure that's ready to flip, ready to acquire strain plastically, but everything is stiff locally, then the strain may not reach there. And so the correlation length would be less, I'm saying, for these brittle materials. I'm just going to leave it there. Let's see what happens, though, when we apply this brittility to the different experiments that we typically run to determine the yield stress. Remembering that this constitutive relation has one really well-defined yield stress that comes from the steady-state flow curve. So if our brittility is 1, we get no overshoots. This is our ductile yielding. If our brittility is higher, we get this rate dependence of our overshoot, even getting sometimes seeing these double overshoots that you might see when you do a steady shear startup. And because our model is reasonably simple to look at, we can actually see that the maximum stress comes from this flow viscosity times the maximum, or times the applied shear rate. But again, because we've got more brittle material, the effective rate that's being felt by the material is lower, which means that the viscosity is higher, which means that the material acquires less strain unrecoverably and therefore more strain recoverably. This manifests itself as an overstretch in the material before it yields. So this overstretching can be measured this is now just the recoverable strain for brittility of 1 and brittility of 20. And so what we see is that when we've got more brittle materials, you actually change the kinematics of how the yielding process takes place. Now we can have a look at creep experiments. Again, if you've got ductile materials, you just see this viscosity bifurcation nearly immediately, whereas if you've got more brittle-like responses, you see delayed yielding. And as another example of this, I'm now showing some more model results, and I'm showing the total strain and then the strain components below, and the total rate and the rate components below. So we see that the delayed yielding that we typically see in terms of the increase in the strain rate at some long time, that increase in the strain rate is all unrecoverable. And the initial response that's decaying, that's completely recoverable. It's like acquiring strain from a Kelvin-Voigt-like solid, and it slows down, and then it starts to yield. So that's what we're breaking those down. And because the model is analytically simple, we can also see that when all of the strain is acquired recoverably, our model now looks like the rate at which the rate would change is dependent on the rate. But now we've got this term in brackets. So this term in brackets, if it was larger than 1, that's when you would see that the rate would increase and you would start to flow, which means that this term below is an effective yield stress, and that the effective yield stress is now enhanced by a factor proportional to the brittility. And that once you start to flow, or once the material starts to acquire strain unrecoverably, that's when you get it going back to just your regular steady-state flow curve. So the reason that we see delayed yielding in brittle materials is that the effective yield stress is raised higher, and it drops down until it gets to the stress that's been applied, and that's when you see the acquisition of strain unrecoverably. Then we can also do the same thing with our amplitude sweeps. Again, I'm showing it for 3 different values of the brittility, and this is in the average responses and the transient Lissajous figures. You notice that there's greater overshoots the more brittle we get, and you can see the unrecoverable parts get much more drastic and abrupt when you have high brittility. Right? And then some other experimental results. This is now a soft glass of star colloids, of star polymers, and you can see that they're slightly brittle, and that experimentally they've got these little overshoots that we also predict from the model just by including this factor of the brittility. We can do it for other materials too, seems to do all right. So where are we? What have we learned from this particular study and all these conversations? Well, we've constructed a single framework that really is viscoelastic in the looks of it. The flow viscosity has a yield stress in it, so it predicts behaviors that are viscoelastoplastic. And we get the amplitude sweep behavior, smooth and abrupt overshoots. We get apparent yield strains from our steady-shear-startup that I didn't talk about. We get avalanche and delayed yielding behaviors under creep experiments. We think we can account for brittility in terms of a ratio of a local to a bulk modulus. And we can determine all of these parameters from simple currently performed experiments. And again, what we've done is we've therefore unified the physics above and below the yield stress with a single set of understandable constitutive relations. And so with that, I'd like to acknowledge support from Anton Parr and the NSF for funding, and all of you for your attention. Sorry for running over time.